Okay, welcome to Fat Loss Part 2. Today we're going to have a chronic changes following training. So what explains chronic change in fat loss? Well, essentially fat loss occurs from fat oxidation exceeding storage. The maintenance of fat mass with regular physical activity must mean that fat intake and storage of dietary fat is balanced by oxidation if we assume that de novo lipogenesis is quantitatively unimportant. So what are the ways that exercise can actually increase net fat oxidation? For one, exercise can increase resting fat oxidation. Two, it can increase fat oxidation during the activity. Or three, it can increase fat oxidation in a post-activity period. So if you look here at this study by Klein, if you look at rest, we see that the black are untrained and the open bar are trained. You see fat oxidation is greater in the trained. After exercise, fat oxidation is greater in the trained, and during recovery, fat oxidation is greater in the trained. So again, fat oxidation is greater at rest, it's greater during exercise and recovery, in untrained versus or in trained compared to untrained individuals. As far as fat oxidation, in general, fat oxidation during exercise should increase fat oxidation overall in a 24-hour period. So that will likely lead to change in body composition. So you see untrained here, you see, to the left. Post-training, at the very top, you see exercise training. You see the light green being an increase in fat oxidation. But you also see that fat oxidation in the darker green to the bottom, fat, is elevated as well following training, because we know you have an increase in resting fat oxidation following training. So if we were to compare some of the dynamic changes that result from exercise, particularly if we were to even look at the transient changes compared to some of the static changes that happen in exercise versus diet only or weight loss only, here's some of the things that we see. So basically what we see is during exercise or after exercise, we see an increase in fat oxidation during and after both training and other physical activity. We see greater non-esterified fatty acid mobilization during and post-exercise. We see increased adipocyte sensitivity to circulating hormones, as well as increased adipose LPL. But the important thing is you're thinking to yourself, oh, but if LPL is going up in adipose doesn't make sense. It's going up more in muscle. So the ratio is skewed towards muscle, and you have a decreased uptake of dietary fat by adipose. You also see increased in IL-6 secretion, which while labeled as an inflammatory cytokine, seems to have a protective effect against fat mass, as well as increasing insulin sensitivity. And we see an increased adipose tissue blood flow. As far as an energy deficit that we get from either diet or exercise, we see altered adipokine expression and secretion. So likely, for example, an increase in adiponectin. We see reduced adipose inflammation, which will improve things like insulin sensitivity. We see increased adipocyte sensitivity to circulating hormones. And we see essentially an increase of resting non-esterified fatty acid mobilization, as well as an increase in adipose tissue blood flow. So there are several overlapping factors between energy deficit and exercise-induced increases in fat oxidation. So let's talk about the regulation of fat oxidation. Basically, the release of fatty acids from adipose tissue during exercise is potentially influenced by adipose tissue lipolysis, the rate of fatty acid reesterification, and adipose tissue blood flow. So those are three different mechanisms. We can increase lipolysis, you can decrease reesterification, you can increase adipose tissue blood flow, and there's a remarkable coupling between delivery of non-esterified fatty acids from adipose and oxidation by working skeletal muscle. In other words, if you deliver it faster to the muscle, you'll likely get an increase in fatty acid oxidation. Now, the other thing to realize about exercise here is that exercise will increase the oxidation of fat following a meal for up to 20 hours. So you can see rest is those bottom graphs looking at fat oxidation, response to lunch and dinner. And then you can see exercise at the top with the red arrows pointing upward. Fat oxidation is increased even at dinner when you exercise early in the morning. We also see that adipose tissue blood flow is increased during exercise, but that's also elevated here for several hours after exercise. In fact, you see 240 minutes later, we still see elevated adipose tissue blood flow. So that exercise bout is going to have a critical impact on adipose tissue blood flow for hours following the exercise bout. One of the important things that I want to emphasize is that endurance training decreases your reliance on carbohydrate as fuel. So if you look at RER from pre-training versus post-training, we see that RER goes down, and we also see fat oxidation goes up. If you look at CPT1, basically which is carnitine palmitoyltransferase 1, what you can see is that in the clear, the open bar, which is untrained, you see its level when you have an increase in training status, meaning long-term training. You notice that CPT1, or carnitine palmitoyltransferase 1, is greater in expression. So basically what that means is that your rate-limiting transporter is greater following endurance training. And that's what CPT1 does, is it's a rate-limiting transporter for taking up long-chain fatty acids into the mitochondria. How do we know this? Well, what you're seeing here is this. So, what I want to point out here is we're looking at essentially, looking at So we're essentially looking at here fat oxidation given 60 with carbs given 60 minutes before exercise. So what you basically see is free fatty acids, which is the top group when you don't give carbs, which is the open bar essentially, and then you see free fatty acids in the dark bars, which is if you gave carbohydrates. So you see fatty acids in the blood are depressed when we actually consume carbohydrates. And then if you look over at plasma insulin, we see that essentially plasma insulin levels when you give carbohydrates, which is the dark bars, is higher before exercise compared to the white bar. Intriguingly enough, if you look at the black bars in insulin, you see that essentially insulin goes down during exercise, but it's still elevated relative to the placebo or the fasted. Why is this the case? Well, we get a counter-regulatory response during exercise, in which epinephrine, norepinephrine, and other counter-regulatory hormones antagonize insulin and depress its release. Okay, now one thing I want to point out is what this slide is basically showing is that if you look essentially at fasting palmitate, which is a long-chain fatty acid, okay, and you look at infused percentage of the infused tracer oxidized to the infused palmitate and look at how much is oxidized, we see about 86 to 87% is oxidized when you're fasting. If you give glucose in palmitate, you see that only 70% is oxidized. So why is that the case? Well, let's explain this in a second. So basically, you cut it down by about 16-17%, the oxidation when you have carbs. If we look at octoinate, which is a medium chain triglyceride, then basically what we see is that you see around anywhere from 94 to 98% is oxidized in a fasting condition. And we see the same thing when you give glucose in octoinate. So why is a medium chain triglyceride not inhibited, but a long chain fatty acid is inhibited? Well, the answer to that question is that medium chain triglycerides are not subject to transport mechanisms such as CPT1. Okay, and insulin inhibits CPT1. Or carbohydrates in general inhibit CPT1. That's why when you combine high fat and high carb, you're inhibiting the ability to transport long chain fatty acids. That's not the case if you actually were to consume medium chain triglycerides, which we see here. So that's the end of the lecture. We're going to get in the next two lectures into more of the applied. I'll see you next time.